Alrighty, so then we're going to be talking about Chapter 3, Data Description today. We'll start off with 3.1, talking about measures of central tendency. Hopefully you remember most of these words, but of course we'll make sure we know how to calculate them as well. So the first objective is to summarize data using measures of central tendency, such as the mean, median, mode, and the mid-range. Measures of central tendency are also called averages. Notice the purpose of each and how to use them to describe the data. So all of them can give us the average depending on, again, what we're trying to achieve in our outcome. So we have parameters and statistics. Recall the definitions of a population and sample. So population, all subjects of interest or being studied. Subjects may be humans, animals, business entities, products, etc. The size of the population usually makes gathering data from every subject difficult due to expense or time. Again, population is everybody. Sample is a group of some subjects selected from the population, right? So we can grab, so if there's 1,000 people in the population, we can grab 100 to 200 to be our sample, and that could be a little bit more feasible, and we hope to get an accurate result of the population from that sample, right? So measures found by using all data values in a population is called parameters. This is key to remember. Parameters goes with population. Measures found by using data values from a sample are called statistics. So again, statistics goes with sample, parameter goes with population. Think of it like this. P goes with P, S goes with S. You'll need to remember that. General rounding rules. In statistics, we typically round only after the final answer is calculated. We don't want to round in the middle of our work. We want to do it at the final results. Again, intermediate rounding increases the difference between the answer and the exact value of the statistic. So we're trying to be as accurate and as close to the population with our sample as we can be. We want to round at the very end if we round at all. So the very first title we're going to get into is the mean. The mean is, again, the arithmetic average. So again, the mean is the arithmetic average found by adding all the values of the data and dividing by the total number of values. Hopefully you remember that from grade school. To do this, we're going to round the calculated value of the mean to one more decimal place than occurs in the raw data. So let's say you get a whole bunch of whole numbers, you're going to round to the tenths place. If you get, let's say you're talking about money, so you get a whole bunch of cents, so you're going to round to the ten thousandths place, the third decimal place. All right, so you always go one more than what all of your original numbers are. All righty, so the population mean, so the entire mean population, will be denoted by mu. Mu is written like a U, kind of like that. That is a mu. All right. Notice that is actually a Greek letter. So again, the population mean denoted by mu is calculated by using all values in the population, and the population mean is a parameter. So anything that deals with population, the entire population will be a parameter. To calculate the mu, you just add up every single sample in the population and divide by how many are in the population. Note that it is a capital N when you're dealing with the entire population. So we take the sum of, this means sum of, meaning we're going to add all of those values and then divide. So again, where X represents a data value in the population. So all these are just certain data values all added up. And capital N represents the total number of values in the population. The sample mean, denoted by X bar, so it's going to be a capital X with a line above it, pronounced X bar, is calculated by using the data values in the sample that you have. And again, the sample mean is a statistic. So a couple of things I want you to note here. Anything that deals with population will have Greek letters. Anything that deals with sample will have what they call Roman letters. But they're typically like R letters that we use, X, Y, Z, A, B, C type thing. Right? You'll see that to find the sample mean is very similar to the population mean, just notation has changed. So X bar representing the sample mean, you'll add up all the X's or the values in the sample, add them all up. So again, sum of, and then now notice here, we're going to divide by little n. Little n is going to represent the number of items or people in the sample. So capital letter N, the entire population, lowercase n, the population within the sample that we're looking at. So again, where X represents the data value in the sample and N represents the total number of values in the sample. So here's where that big point comes in. In statistics, Greek letters denote the parameters. So that's your mu's or any other type of Greek letters. And what they call Roman letters denote statistic. Your Roman letters are your everyday typical letters. Assume that the data are obtained from samples unless otherwise specified. So if you're given a set, we assume it is just a sample unless they tell us, hey, this is the entire population of this object, right? They got to tell us that. All right, so let's look at our first example. In example one, salaries of colleges and university coaches. We saw this in the previous chapters. It says the data are salaries in hundreds of thousands of dollars of a sample of 30 colleges and university coaches in the United States. We're going to find the sample mean and use the technology of our choice, right? So here is the numbers again. We want to know what is the sample mean of the college and university coaches. So all you got to do is simply just add those all up. All right, there's 30 numbers. So I'm just going to pull up a regular calculator. And I'm just going to start from the top left. My first row is on that upper page. So I'm going to start with 164. And I'm just going to go from left to right, top to bottom. And I'm going to use my finger to help me know when I've done each one. I have a pattern so you don't forget any numbers. Right now it's just 30, but it can get a lot more. Later on in this chapter, I'll show you a way we can use our TIN spires to help us calculate a lot faster. But for now, let's just do it by hand. So 164 plus 225 plus 225 plus 140 plus 188 plus 210 plus 238 plus 146 plus 201 plus 544 plus 550 plus 188 plus 415 plus 261 plus 164 plus 478 plus 684 plus 330 plus 307 plus 435 plus 857 plus 183 plus 381 plus 275 plus 578 Let me get to my last numbers on a different page. Plus 450 plus 385 plus 297 plus 390 plus 515. And we get 10,000. Let me write this number down. So we get 10,404. To find this sample mean, I'm going to take that sum. So this again, this was basically your sum of x right here. And now I'm going to divide that by the little n, which was the number of samples. So in this case, there was 30 coaches. So we're going to divide it by 30. So we take this number, divide it by 30, and we get 346.8. Again, we're going to round to the tenths place due to the fact that all of those were whole numbers. So we want to round one decimal over. Had you got a perfect whole number, you would just want to say 0.0. That's just indicating how accurate your results are. Right? So that means the sample mean that we have of 30, the average college university coach gets paid $346,800. So if you need some career advice, that seems to be a good one. All right. So hopefully that wasn't too difficult. It can get tedious in this work, but the math itself isn't too bad. All right, in previous chapters, we constructed a frequency chart with 8 classes for this sample. We're going to use the frequency chart to calculate the mean for grouped data. The process is most frequently used when the raw data is not available. So again, if we don't have the population, sample mean is where we go. So again, note here, we are dealing with a sample since this is a sample mean. And what we're going to do is when we have frequencies, we will do the amount of frequency times the midpoint of our class boundary. And then we're going to add all of those numbers up and divide by how many we had. So you would have to add up this frequency chart. All right. So again, where F is the frequency, XM is the midpoint. All of this is done for us. We actually did this in a previous chapter. So that's why we're not doing this part again. We're just taking another step with it. All right. So here we go. So what we're going to do is we're going to take our frequency and we're going to multiply it to our midpoints. And then we're going to write all these results, add all of these results here. That would give us the sum, and then divide it by the 30, which is the number in the frequency. Again, with 30 universities. And you'll see that you should get the same or roundabout the same answer. All right, so here we go. So I'm going to do 11 times 184.5. And I see I get 2,029.5. Then I get 5 times 274.5, which will give me 1,372.5. Then I'll do 4 times 364.5, which tells me I got 1,458. Then I'll do 4 times 454.5, which gives me 1,818. Then I'm going to do 4 times 544.5. That gives me 2,178. Oh, this one's super easy. 0 times this will just be 0. And then 1 times these are going to be 724.5 and 814.5. All right, my next step is to now add all of those numbers up. So I'm going to go 2029.5 plus 1372.5 plus 1458 plus 1818 plus 2178 plus 724.5 plus 814.5. All right, so then we get a grand total of 10,395. If you recall our last number, which I don't have it written, I had it written down earlier, I think it was about 404. So we're only off by like 9. So that's pretty good. Let's see how accurate our result will be. So then you want to take this number and where it says find the sample grouped mean for the frequency chart, again with the capital X bar indicating the sample mean, all we're going to do now is take this final number and divide it by 30 for our frequency usage or the amount of coaches we had, and we get 346.5. So 300. See if I can kind of keep it. Yeah, right there, somewhere like that. So again, that would give us 346.5. Right? And when we did it just straight up adding the numbers, we got 346.8. So having that tenths place decimals, again, just tells the reader how accurate we are. We are accurate to the ones. The tenths place could be different from all of our different results depending on the process that we calculated. But that is another way. Again, maybe you have the class boundaries and the class midpoints and the class limits versus having the 30 numbers. So let's say, again, you didn't have 30 numbers, but they gave you this. You can calculate the correct mean as well. All right, so now we're going to compare the sample mean calculated from the raw sample data and from the grouped data in the frequency chart. Note the mean is not always an actual data value. And what that basically is stating there, the mean can sometimes always be an actual value, and it cannot always be the actual data value, depending on how large your sample is compared to how large your population is. So, in my opinion, it is more accurate to say the mean is not always the actual data value. All right. So let's review what we've learned so far about mean, and then we'll get into the next central tendency. So all the different properties of mean. So far, we found out that the mean is found by using all values of the data set. The mean of a data set is used to compute other statistics. Such as the standard deviation. And we'll talk about this in a little bit. The mean of the data set is not necessarily one of the data values. Okay. So it can be, and it cannot be, but it's not necessarily one of the data values. Very rarely do you get the mean and it happen to be someone's, like in that instance, someone's coach's salary. But really and truly, if you have a small sample, it could potentially be. There's not much there. All right, to find the mean of a frequency distribution, there must not be an open-ended class, meaning the boundaries need to be precise, 180 to 190. It can't be like 180 and more. and then it becomes open, and then a lot of data can be thrown back into it. It has to be ended, mainly because you have to find that midpoint. So if I have 180 or greater, I don't have a midpoint for that class. So it has to have boundaries. So 180 to 190, 191 to 210, or whatever the case might be. All right. So, and then number 5, the mean is affected by extremely high or low values, and we're going to call those guys outliers. So again, we'll talk about more of this later on, but if I have really high values or really low values, the mean will be adjusted by that. If it's a high number, the mean is going to be a little bit higher than normal. If it's a low number, it's going to bring it down. All right. So that is the properties of mean. So let's get into median. Easiest thing to remember about median is the middle number. All right. So there you go. So the median is the center or middle of an ordered list of the data array. So you have to put the numbers from least to greatest, and then figure out what the exact middle number is of that data. And now you have the median. The median symbol can either be MD or MED, right? I typically see more MED, but you could see MD in your textbook as well. All right, so to find the median, we're going to arrange the data from smallest to largest. Be completely honest with it, it doesn't matter if you go largest to smallest. We just typically always go smallest to largest. 2, we're going to determine the number of values in the set, so figure out how many numbers are in the sample. 3A, if n is odd, the middle data value is the median. If n is even, the median is the mean of the middle two values, meaning if you have an odd number, you'll land on a number. So you'll have like 5 numbers on one side, 5 numbers on one side, and the 11th number, the one in the middle, will be your median. Versus if you have an even number, you'll have 5 and 5, there's 10, so there's not a number in the middle. So what we do is we find the mean or the average between the two numbers 5 and 6 to find that average. And I'll show you some examples of that here in a second. All right, so in example 2, we're going to look again at that calories per ounce of salad dressing. So in the previous chapter, we ordered the data for a sample of calories per 1 ounce of 36 salad dressing. So we did this work already. We're not going to have to do it again. So it's a nice order for us. And we're going to find the median of this data. So I want to try to get, there's all the data. So best way to do this, you have 36 samples here. So what we want to do is cut that in half. Half of 36 is 18. So I'm going to go 18 numbers. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So here's my 18th number, right? That also means I can go 18 from this side, and you'll see what will happen. So I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I don't typically go from the end up here. Usually I'll just go to 18, I'll be done. But I want you to see what happens is that this right here ends up being the middle of the data. So you have to find the number in between these two numbers. Now, what's really nice is the number in between these numbers happens to be 130, but the math right here would be 130 plus 130 divided by 2. So it's 260 divided by 2, which is 130. Now, I just showed you the math so you could see it just in case it ever is not the same number, how to actually calculate it. But in this case, the number that's between these two would be 130. So the median of this data is 130. Right. Again, I wouldn't go both ways. I just want you to see why I went to 18 and cut it in half, so it would be the exact middle. All right, so let's look at another example. So in example 3, it says the number of tornadoes per year. So the National Oceanic and Atmospheric Administration, or the National Center for Environmental Information, reports the number of tornadoes per year. So we have a small set, but we do need to put this from least to greatest. So it looks like my smallest number is 878. Then it goes 881, then 891, then 1156, 1282, 2192, one. Oh, nope, I lied. Hold on. There's a 16 there. So that'd be 1625 and then 2192. All right, so then I go, all right, I have 1, 2, 3, 4, 5, 6, 7 numbers. So half of 7 would be 3.5. So that means I just need to go to the fourth number. So I'm going to go 1, 2, 3. There's my number. If you don't trust it, you can always go from the other side as well. 1, 2, 3, 4. There's my number. So that would be the middle number. So when it's an odd number, the median is one of the set data. If it's an even number, we have to do the average between the two numbers in the middle. All right, so those are your two examples of that. So let's review real quick about medians so far. So it says the median is used to find the halfway point or midpoint of a data set. The median is used when one needs to determine if a data value falls in the upper half or the lower half of the distribution. And we'll talk about that when we look at different type of bar charts that will lead into our box and whisker plots. The median is not affected very much by outliers. So if I was to throw in really big numbers or really small numbers, it is not going to be affected because it's just the middle number. So if you add another number to the end, the number itself will, yes, will shift a little bit, but it's not going to be shifted towards the big number or the small numbers. It's going to be shifted more in the middle of the data. So it's not affected by outliers. It'll just be affected by more numbers. The median can be used with open-ended distribution. So if I did have something where it's like 180 or more, I could still use that data because I'm not looking at midpoints. All right. So there is your mean, your median. So let's talk about mode. So again, mean, average, median, middle. Mode is usually remembered by most occurring number. So the mode is the value in the data set that occurs most often. So mean, average, median, middle, mode, most. That's how we kind of remember it here. Data sets that have only one value that has the greatest frequency are called the greatest frequency are called unimodal. So if we typically have the mean happens to be the mode, and the mode is the most frequency, it's usually unimodal because it has that one high point of that of values. All right. So let's look at an example here. So in example 4, it says find the most of a unimodal sample. So the mode here, a lot of times people put this from least to greatest as well, and I think that's what I'm going to do to kind of help us out. So let's see. So this would be, looks like 10, cross it out, another 10, cross it out, 10, cross it out, 11.3, 12.4, 14, 18, and then 34.5. All right, so then to find the middle, or sorry, the mode would be most often, I can obviously see that 10 is the most often number. Maybe you could see that without putting it from least to greatest. More data might need you to do that as well. So there is one mode in this situation. There's only one number that has the most occurring. So the sample is unimobile. There are different types in a situation in which you could have a few of them be the same amount of mode as well. And we'll look at those. So 10.0, because again, that's what we need to use, is the 10.0, occurs 3 times, which is more than any other data value. All right, so that right there is its one and only mode. All right, so data sets do have data sets that have exactly 2 values that occur with the same greatest frequency are bimobile. So if we only have one mode, it is unimobile. If we have 2 modes, meaning we have 2 numbers that occur the same amount of times, it is called bimodal. So let's look at an example of that. So again, I like to put it from least to greatest, just so I can kind of see my data. It looks like 104 is the smallest, so 104. Then I have another 104. Then I have another 104. Then I have another 104. And then I have a another 104, followed by a 107, a 109, another 109, another 109, another 109, another 109, followed by a 110, a 111, another 111, and then a 112. So looking at this, I can see we have 1, 2, 3, 4, 5 104s, 1 107, 1, 2, 3, 4, 5 109s, 1 110, 2 111s, and 1 112. So I can see this one will have 2 answers. It'll have 104 and 109 since it has exactly the same greatest frequency. So again, when a data set has more than 2 values that occur with the same greatest frequency, it is called, oh my bad. This is the answer here. This is on a different one. So when a data set has more than 2 values that occur with the same, it is called multimobile. So again, this right here is bimobile up here on the example we just did because that's 2. But if I was to have more than 2, we have multimodal. So let's look at that example. So in example 6, using example 2, 3 values occur 6 times with the greatest frequency, which means the data set will become multimodal. And if you're looking for those sets, it would be 1, 2, 3, 4, 5, 6. This is 5. 1, 2. This is 2. 1, 1, 2, 3, 4, 5, 6. This is 6. 1, 2, 3, 4, 5, 6 is 6 as well. 1, 2, 3, 4. 1, 2, 3. 1, 2. 1, 2, 3, 4, 5, 6, and then 1. So you can see I have 2 numbers, 120, 130, and 160 that occurred the greatest amount of times. And when you have if you have more than 2, it is multimodal. All right, so again, we've talked about unimobile, bimodal, and multimodal. There is situations where there isn't any mode at all, meaning every single number happens the exact same time. Oh, I didn't realize there was a solution there, but this would have been 3 followed by 120, 130, and 160. But there you go. But there are situations where there is no mode, meaning they all occur the same amount of time. So some data values have no mode at all. And again, this happens when all values occur at the same frequency. So if we use example 3, all values in the sample occurred exactly once. There was no repeat numbers, so therefore the data set has no mode. The mode is only measure of central tendency that can be used to find the most typical case for a nomial data set. All right, if we look at example 7 here, and this comes from chapter 2 as well, we have nomial data for the worldwide sales in billions of dollars for fast food franchise for a specific year. So when you're looking at situations like this and you're looking for the mode, the category with the greatest frequency would be the mode. So that would be 14.2. So that would be KFC. So when you're given a frequency chart, mode would be the highest frequency. Thus, the most typical case here is sales of 14.2, meaning the mode is KFC. So since KFC had the highest greatest frequency, then the mode would be KFC as well. All right. So that's what you do if you're given a frequency chart. So let's review mode real quick. So if we review properties of mode, the mode is used to find the most typical case. If there's a lot of mode, we can kind of see what our distribution is going to look at. The mode is also the easiest average to find. Again, we're just looking at what occurs the most, not much math with that. The mode can be used for qualitative and quantitative. So I could be looking at, I don't know, the color that shirts people wear, and I could see that the mode might be blue or red or green or whatever the case might be. And I can easily identify that also with mode. And then the last one, the mode is again not necessarily unique and may not even exist. So again, we've seen it, modes have one, we've seen modes have two answers, we've seen mode have more than two answers, and we also seen where mode didn't have an answer at all. So it's not unique, and it also might not even work. Now, there are some modes that are unique, it only has one answer, but not every situation. All right, so let's look at example 8 here. Nope, my bad, this is just a little notes. We'll look at 8 here in a second. So resistant measures of central tendency. So the measures in resistance when an extremely high or extremely low data value does not change the value of the measure. We've seen that the median and the mode are not affected by these extremely low or extremely high numbers. So again, median and mode are resistant. However, extreme values, also called outliers, can have a striking effect on the mean. So the mean can highly be affected by the extremely high or extremely low number since we're adding them all up. We'll learn how to determine which values are outliers in a later chapter. So sometimes people just like to look at it and go, then it has to be an outlier, but there is a mathematical process to determine does that data value set outside the outlier range. All right, now let's look at example 8. So we're going to put this all together now. And we're going to find the measures of central tendency. So the following data set has a value much higher than the rest. So here's one set. When the large value is deleted from the data set becomes this. So what they did is, I think, 240 was in this set. They took 240 out. We want to see what effect does that 240 have on all of the central tendencies. So again, we're going to find the central tendency, then compare and contrast the values. So the measures of central tendency for the first data set follows. The mode, where we go. All right, so I'm not seeing any repeat numbers, but let me just write it out anyway. So 122, looks like 140, 141, followed by 149, followed by 153, 155, 162, 165. Oh, I lost the 157 there. So I'm actually going to come back. A 157 here, followed by that 162, 165. So that's why we mark things out so that we can see if we lost some numbers. So 177, 189, and then 240. And I'm not going to do these next six. I know this will be the exact same, just without the 240. So the mode, I can obviously see there is no mode. No repeated numbers. The median, so there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So again, if I do 11 divided by 2, I get 5.5. So that means I need to go to the sixth number. So 1, 2, 3, 4, 5, 6. And again, if you don't trust it, 1, 2, 3, 1, 2, 3, 4, 5, 6 lands right there. So my median here is 157. The mean, let's add that up real quick. So that was 122. Actually, I tell you what, I'll just add the bottom one since it's not marked up. So 177 plus 153 plus 122 plus 141 plus 189 plus 155 plus 162 plus 165 plus 149 plus 157 plus the 240. That gives me 1810. And then I'm going to divide that by 11. And because those are all whole numbers, I just need to round to the tenths place. So I'm going to write it here. The mean, I know it's on y'all's next page, is 164.5. Because then that 4 tells that 5 to stay the same. All right, so there we go there. So there's the mean. So the measure of central tendency for the data set without the higher values are. So tell you what, let me go back up and I'll bring all that stuff back so I can kind of compare both of them. It's on your page as is. There you go. So for me, I'm just going to do this right here. So the mode, again, looking at the next result, did not change. So there's still no mode. The median this time would be 10. So 10 divided by 2 would be 5. So I'd go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I need to find the average here. So I need to go 1. Oh, my bad. I need to do this one. So if I go 1, 2, 3, 4, 5, that would be 155. And then 1, 2, 3, 4, 5 plus 157. Add those up, divide by 2. That looks like that's going to be 156. So my median now is 156. So one number difference. My mean though, so this is what I'll do with my handy dandy calculator. I'll take that number and I'll multiply it by 11 to go back to my original set. And now I'm going to subtract 240 from that. And now divide that by 10. And I now see that my mean is 157. So you can see a dramatic change in the mean went down by 7.5 points versus the median got affected by one number. And then the mode didn't change at all. So again, there's the answers. I just wanted to keep the data there. So again, there's your no mode, 156 for the median, and then the mean was 157. So we notice how much the mean changed. The mean is higher for the original data set and lower for the edited data set, and how close the median of the edited data set is to the original value. So again, it was literally one number off. Again, it's only affected by how many numbers there are, not if it's a high number or a low number. All right, so that is pretty much, again, your mean, median, and mode. The next central tendency is called the mid-range. So the mid-range is the arithmetic mean of the lowest and highest values in the data set. It is the midpoint of the range. It is not efficient nor resistant. However, it can estimate the center for a uniformed distribution. So if you know the data is uniformed, then you can calculate the mid-range, and it can kind of help you calculate things. But mid-range labeled with capital M, capital R, you simply just take the lowest value plus the highest value and divide it by 2. So again, looking at example 9, we're going to find the mid-range of that data set, of the original and the new. So again, the original, the lowest, believe, would be, is that 122? I think that's right. So 122, I believe, was the lowest. And we're going to add that to the highest value, which is 240 in this example, and then divide by 2. Let's pull up our calculator. So that's 122 plus 240. Divide that result by 2, and we get 181. So the mid-range of the original data is 181. So that kind of gives us an idea of where the average might be. Then we can do the same thing with the edited data, this time 122 plus the largest number this time would have been, is that 189? Looks like 189. So 122 plus 189 divided by 2. So now let me go back over here. I'll do 122 plus 189, divide that by 2, and I get 155.5. So 155.5. So you can see the mid-range is definitely affected by by outliers. If the outlier is the highest or the lowest, the mid-range is definitely affected. So with that, let's talk about these type of numbers here. So 181 and 155, let's see if I can keep them there for a little bit. So I guess the question here, I have to delete it because I can't really see. Is it reasonable to use the mid-range as a descriptive statistics for this data set? And really and truly, you have two-part answers. We got 181 as our original data. So you could not use the mid-range for the original data, but you could use it for the new data. Since the new data gave us a mid-range of 155.5, and I believe our average was 157. So that could be used as central tendency when taking. So a couple of properties about mid-range that we've seen so far. The mid-range is, again, easy to commute. It says smallest plus largest divided by 2. The mid-range gives the mean of the range of the data set, so the average of the actual range. The mid-range, though, was affected by outliers. So we saw in the first set, it was 181. That's very affected and wasn't close to our mean at all. Versus when we took the outlier out, our mid-range was a lot closer to our mean. All right, so let's talk about shapes of distributions now. So in chapter 2, many different shapes of distributions were discussed. The 3 most important shapes to consider are those that are positively skewed, symmetric, and negatively skewed. For positively skewed, or what we also called right skewed, so if it's positively skewed or right skewed distribution, most of the data will fall on the left of the mean and cluster at the lower end of the distribution. The tail stretches out to the right. So again, the mean will be to the right of the median, and the mode will be on the left. The mean is pulled towards the tail by more extreme values. So you can kind of see here. So for a positive skewed data or right skew, so this is a positively skewed. And then we know that this is a right skew because the tail pulls to the right. The most of the data falls on the left. So these are why it's right skewed is this data on the right is pulling the mean. The mean should be closer to the median right here in the middle of the data, but these numbers are pulling it to the right. That's why it's right skewed. That's why the tail stretches to the right. But you can see also on a positive skewed or right skewed, the mean is to the right of the median, and the mode is going to be to the left of the median. So all the median and mode is to the left of the mean because the mean is being affected by this outlier here. All righty. So for the next big one is the negatively skewed or left distribution. Most of the data falls to the right of the mean and clusters at the upper end of the distribution. The tail stretches out to the left. The mean will be to the left of the median and the mode will be to the right. As before, the mean is pulled towards the tail by the most extreme value. So let me again show you that as well. So I know this is left skewed because now the data on the left side is pulling my data. So therefore, this is a negatively skewed. So I'm pulling it to the left. And when that happens, you can see again, the mean now is to the left of the median and the mode. Median again being the middle, mode being the most occurring. But again, the mean should be closer to the median, but because of these outliers, it is pulling the data to the left. All right, and then we have a third one. This is what is ideal. And this is what we'll probably play around with for most of the rest of the other chapters. But for symmetric distributions, the data values are distributed evenly on both sides of the mean, and then the distribution is unimodal. With the mean, mode, and median are equal and at the center of the distribution. So you can see a unimodal, perfect set of data, very even. The mean, median, mode are pretty much all the exact same number. All right, I was actually going to do an entire video over chapter 3, but I think I'm going to chunk this and I'm actually going to do it by section. So this will be the 3.1 video, and then I'll do one for the other 3 sections as well. See you in the next video.